Welcome back, ladies and gentlemen. We will continue our journey to explore sets and their properties, and today we are going to learn about power sets, which are a very important construction in set theory, and we're going to learn about the cardinalities of sets, which is a means of comparing the sizes of different sets. The contents for today's video are the following. First, we will introduce the notion of cardinality for sets. Then, in turn, we will study finite sets, infinite sets, and finally, we will learn about power sets. As usual, please like this video and subscribe to my channel to support me making further content in the future. We will begin by studying the cardinality of sets. And this is its definition. A set X is called finite if either it is the empty set or if there is a bijection from the set X to a set of the form 1 to n. So the set containing the numbers from 1 to n. And in this case, we say that the cardinality of X is, well, 0 if it's the empty set, and n if there is a bijection from X into the set of the numbers from 1 to n. There are other notations for this that are often used, and I probably will use sometimes too. So one is to write the set X enclosed in these two bars. As you may know the notation from absolute values for numbers, or sometimes you use this hash symbol in front of the set to indicate the cardinality. Now, what this means, of course, is that the cardinality should somehow say that this is the size of the set X. So if our set is empty, it has 0 elements. That's why we set the cardinality to 0. And if we have a bijection from X to the set of elements 1 to n, we can think of it as an enumeration of the elements of X. So we think of it as having n elements then. And this is reflected in setting the cardinality of X to n. Well, you might have noticed that this definition does not exclude the possibility that there could be bijections from the set X to different sets 1 to n, and say the numbers from 1 to k, where k and n are two different natural numbers. So it is not clear that this cardinality is actually a uniquely defined number. But in fact, this cannot happen, and we will see this later, that there is precisely one n, such that such a bijection from x to 1 to n exists, if there exists such a bijection at all. And this means this cardinality, which we define here, is in fact well defined, so there are no ambiguities about this definition. Let's look at an easy example first. So here we have the set X containing the card suits, heart, spade, diamond, and club. And this has cardinality 4. It has 4 elements, and formally we could say we define a bijection mapping the heart to number 1, the spade to number 2, the diamond to number 3, and the clubs to number 4. That would give us a bijection, and then by definition we could say this set has cardinality 4. As another example, let us look at two finite sets AB, and then the Cartesian product A times B is also finite and has cardinality A times cardinality B. So recall that I already mentioned in the last video that this notation here, A times B, is suggestive of the fact that this Cartesian product contains as many elements as the product of the number of elements in A and the number of elements in B. And more generally, if we have a Cartesian product of more than two sets, A1 times A2 times AN, so let's say there are n finite sets, and we take the Cartesian product of them, then the cardinality of the product is simply the product of the individual cardinalities. So this product has as many elements as the product of the number of elements in each of its component sets. And to see this, you do a little bit of a combinatorial investigation. So this set here, this Cartesian product, consists of all the n tuples of the form a1, a2, up to an, where each entry ai is taken from the ith set in this product. And now for each entry we have cardinality of ai choices. So we have as many choices for the first entry as there are elements in a1. So that's cardinality a1 choices for the first entry. And then for each of these possibilities we have again as many choices for the second entry as there are elements in the set A2, so that's cardinality A2 choices. So we have cardinality A1 choices for the first entry times cardinality A2 choices for the first two entries, and so on until at the end we can say that the possibility of choosing such an n-tuple with entries in these sets is the product of the cardinalities of the individual sets A1, A2 up to an. Now what happens if a set is not finite? Well, then we call it infinite. A set X is by definition infinite if it is not finite. So if we cannot find a bijection from our set to one of the sets of numbers from 1 to n, then we can say that X is infinite. And unsurprisingly, the sets of natural numbers, of integer numbers, of rationals, and of real numbers are all infinite. Intuitively, this is completely clear to you, but we will give a proof of this fact later. And we will learn more about infinite sets later, but now we first study the properties of finite sets, and many properties of finite sets are intuitively obvious, but it can be quite surprising how complicated their formal proofs are. Now we get to study finite sets, and we're going to prove some facts about finite sets that, as I said, will seem completely obvious to you. But keep in mind that we gave a very simple definition for finiteness of a set, and by proving these seemingly obvious statements, we make sure that our definition of finiteness is in harmony with our intuition on finiteness. We begin with Theorem 6, and as I said, this will seem completely obvious to you. Let X be a finite set, and then every subset of X is also finite. For the proof, first consider the case that X is the empty set. Then there's of course nothing to prove, because the only subset is the empty set itself, which is finite. So suppose that X is not the empty set now, and let S be a subset of X. Again, if this subset is the empty set, there's nothing to prove, so we suppose again that the subset S is also not empty. Since X is finite, this means by definition that there exists a bijective map F from the set X into the numbers from 1 to n for some number n, the cardinality of X. Now we consider the restriction of this bijection F here to the subset S. So this is a map from S into the numbers from 1 to n. And since F is bijective, this restriction to the subset S is injective. We write A for the image of the restriction of F to S. So A is a subset of the numbers of 1 to n. And then we get a bijective map by looking at the restriction of f to the subset S to its image, to the set A. And now I make the claim that A is finite. So we take this as given for the moment, that this image of f restricted to S is finite. And so that there exists a bijection from A into the numbers from 1 to k for some number k in the natural numbers. I call this bijection G. And then I can compose G with f restricted to S. So I get a map starting at S, and it maps into the numbers from 1 to k. And this composition is a bijection because both f restricted to S is a bijective map to A, and because G from A into the numbers from 1 to k is a bijection because we take A to be finite. And the composition of two bijections is again a bijection. But this means having a bijective map from S to the numbers from 1 to k, that S is finite. So we have shown that the subset S of X is finite, given that our claim here holds. So the proof is complete once we prove the claim that this set A is finite. And notice what I actually did here. I reduced our original problem on subsets of arbitrary finite sets to a special case, namely to the proof that a subset of the set of numbers from 1 to n is finite. And this is what I'm going to prove now. And once this is proved, the proof for this theorem here will be complete. So I prove now that every subset of the set of numbers from 1 to n is finite, and then the subset A in the previous proof will follow to be finite from that. I do this by induction on n, so by induction on the numbers in my set here. The initial case is the set 1, the set that contains only the number 1, and it has subsets 1 and the empty set, and both of them are finite. So the initial case holds up. Now our induction hypothesis is the following, that for some number n greater or equal to 1, all the subsets of the sets of numbers from 1 to k are finite for all the k from 1 up to our particular number n. And now in the induction step, I consider the set of numbers from 1 to n plus 1, and I take a subset A of the numbers from 1 to n plus 1. And I want to see that A is actually finite. Now, if the element n plus 1 is not contained in A, then A is already a subset of the numbers from 1 to n. And then we can just use the induction hypothesis to conclude that A is finite. We're done in this case. So otherwise, A does contain the element n plus 1. And then I can look at its complement, of the complement of n plus 1 in A. So I call this B. This is set A without the element n plus 1. And A is then clearly the union of the set containing n plus 1 and B. Now, this means B is a subset of the numbers from 1 to n. And by the induction hypothesis, B is finite. Because B is finite, there exists a bijection, I call it FB, from the set B into the numbers from 1 to k for some k. And now I define a map that's going to be the bijection for my subset A. I define it as follows: f going from A into the numbers from 1 to k plus 1, where k is the one I took from the bijection for B here. And what I do is, any element from A gets mapped to FB of A if it is contained in B, if it's contained here, or if A is equal to n plus 1, which is not in B, then I map it to k plus 1. And this map F is a bijection. Now this is not too difficult to verify, so it is injective on B because by assumption FB is injective here. And on the only element n plus 1 that is not contained in B, it assumes a different value than any element of B would. So F is injective, and it is also surjective because FB has all the numbers from 1 to k in its image, also by this FB being a bijection. And then the only missing one in this set here is k plus 1, but the element n plus 1 is mapped to k plus 1, so all of the numbers from 1 to k plus 1 appear in the image of F, so it is surjective as well. And that makes it a bijection. So we have a bijection from F into the set of numbers from 1 to k plus 1, and that means A is finite. So in any situation here, the subset A of the numbers from 1 to n plus 1 is finite, and then by induction it follows that this generally holds for all the sets of numbers from 1 to n. Next, we prove one of the most important theorems on finite sets, the so-called Pigeonhole Principle. And this is stated as follows. We have two natural numbers, m and n, and we take m to be larger, strictly larger than n. And we are given a map f from the set of numbers from 1 to m to the numbers from 1 to n. And this f is not injective. So this statement is called the Pigeonhole Principle because if you think of having n holes for m pigeons and you have more pigeons than holes, then if you distribute these pigeons over the holes, then at least one hole must contain more than one pigeon. And this containing more than one pigeon means that the distribution, so the function that does it, is not injective. And before we prove it, we observe this important consequence, and it allows us to finally see that the cardinality of sets is well defined, because if a set X had bijections into the numbers from 1 to n and into the numbers from 1 to m for two different numbers, m and n, say m being larger than n, then this would also give us a bijection between the numbers from 1 to m and the numbers from 1 to n. But the Pigeonhole Principle forbids the existence of such a bijection because it can't even be injective. So in particular, it can't be bijective. And that means the cardinality of a finite set is a unique number, and thus the cardinality is well defined. And this is what I state here in the corollary 8. So a corollary in this course usually denotes a consequence that can be quickly derived from a previously established theorem or proposition. And if X is a finite set, it states, then there's precisely one n such that there exists a bijection f from X into the numbers 1 to n. And this n is the well-defined cardinality of X. But enough on this. Now we're going to prove the Pigeonhole Principle. And again, we use induction on n. We use induction on the size of the smaller of the two sets here. The initial case is n equal to 1, and that means by assumption m is larger than n, so m is larger than 1. So the set from 1 to m contains at least two elements. Let's call them I and j. And then for any map from the numbers from 1 to m into the set that only contains 1, we must have that every element is mapped to 1 because it's the only possibility. So fi is 1 and fj is also 1, but then f clearly is not injective because these two distinct elements assume the same value under f. Our induction hypothesis is now that there is some number n greater or equal to 1, and for all m greater than this n, and any map f from 1 to m into 1 to n, this is not injective. The induction step, we go to n plus 1, so we look at the numbers from 1 to n plus 1. We take some m that is strictly larger than n plus 1, and we suppose there is a map f from the numbers from 1 to m into the numbers from 1 to n plus 1. We will show that this f is not injective. Now, if n plus 1 is not contained in the image of f, then in fact f is a map into the subset of the numbers from 1 to n, which is a subset of this one. And then we can already apply the induction hypothesis to conclude that f is not injective. So otherwise, we assume that n plus 1 is contained in the image of f. That means there is some number k between 1 and m that is mapped to n plus 1 under f. Now, if there's some other number j in the numbers from 1 to m that is different from k but is also mapped to n plus 1, then f is not injective because we have two distinct values mapping to the same element. Then by definition f is not injective, and we're done. So the last remaining case is that we assume that f of j is not n plus 1 for all numbers that are different from k. And as before, f of k is n plus 1, but all j that are different from k do not get mapped to n plus 1. Now I construct a bijection as follows. A is the set of numbers from 1 to m, but without the element k that is being mapped to n plus 1. So I take this element out of 1 to m, I call this set A, and then I define a map B from the numbers from 1 to m minus 1 into this set A here. And I do it as follows. For all the numbers here that are smaller than k, I just map them to themselves because they are also contained in this set here. And for all the numbers that are greater or equal to k in this set here, I map them to themselves plus 1. And these are also contained in the set A because by doing this I miss the element k, and that's the only one that was excluded from the numbers from 1 to m. And this map B is injective. That's quite easy to see because, well, all numbers j either get mapped to themselves or themselves plus 1, so two distinct numbers get mapped to distinct numbers in A. Now the composition f composed with B is a map from the numbers from 1 to m minus 1 to the numbers from 1 to n. Okay, so B maps 1 to m minus 1 into A, and now f maps the set A, which is a subset of the numbers from 1 to m, into the numbers from 1 to n plus 1, but we already assumed that only k is mapped to n plus 1. So since k is not contained in A, it cannot appear as an input value for f in this composition here. So f, if it only takes input values that come from A, so from the image of B, then it will only assume values in 1 to n. Now, by assumption, our assumption is m is strictly larger than n plus 1, so m minus 1 is strictly larger than n plus 1 minus 1, which is of course n. The induction hypothesis implies that f composed with b is not injective. Okay, we can apply the induction hypothesis because this maps to the numbers from 1 to n. And n minus 1 is strictly larger than n. So the induction hypothesis applies, and we can conclude that this is not injective. But this means there exists elements I and j in the numbers from 1 to m minus 1 that are mapped to the same element under the composition of f and b. So f of b of I equals f of b of j. But b is injective, as we just observed here. So bi and bj are distinct elements, and at least if I and j are distinct, and this means f is not injective because f maps these two distinct elements to the same output, and that means f is not injective, and that is what we set out to prove. So we have shown that this map here, f from 1 to m going to the numbers from 1 to n plus 1, is not injective if m is strictly larger than n plus 1. And thus we have proved the pigeonhole principle by induction. And we can use the pigeonhole principle to prove that certain sets are not finite. Now, as promised, we prove that these number sets are not finite. So Theorem 9 states that the natural numbers, the integers, the rationals, and the real numbers are infinite. And I only do the proof for the natural numbers because it's the same proof essentially for the other ones. We do this by contradiction. I suppose that n, the natural numbers, is a finite set. Then, by being finite, there must exist some natural number n and a bijection b from the natural numbers into the numbers from 1 to n. Now I pick any natural number m that is larger than n. Such a natural number always exists. For example, n plus 1 is always larger than n. And I restrict b, this bijection here, to the subset of numbers from 1 to m, which I can do because the natural numbers contains as subsets all of these subsets of numbers from 1 to m. Now the pigeonhole principle tells me that this restriction, b restricted to 1 to m, is not injective. But if b restricted to a subset is not injective, then b overall can't be injective. But this contradicts b being a bijective map, because a bijective map in particular has to be injective. So we arrived at a contradiction, and our assumption that n is finite therefore must be false, and this means n is infinite. We prove some more properties of finite sets now that are quite helpful in dealing with them and confirm our intuitive understanding of the notion of finiteness. So x and y are finite sets, and then they have the same cardinality if and only if there exists a bijective map between the two. So we have an equivalence to prove here, and what I will do, I will split the equivalence in two implications. So first I will assume that the two sets have the same cardinality, and from this show that a bijective map exists, and then I will do the other direction, assuming I have a bijective map, and show that the cardinalities must be the same. For the first direction, I assume they have the same cardinalities. That means both x and y have bijective maps going from x into the numbers from 1 to n, and also from y into the numbers from 1 to n for some number n, which is the cardinality of both of them. And then we can define a bijection f from x to y as follows. well, this image suggests what we do, and recall that by being a bijection is equivalent to by having an inverse map according to a theorem we proved in the last video on sets and maps. And what I can do now is to get a map that is a bijection from x to y, I go with the map bx into the set of numbers 1 to n, and then I take the inverse map of by to go from this set into y. And the inverse of a bijection is of course also a bijection, so the composition of by inverse with bx is a bijective map from x to y. So it completes this little diagram here. And this way I have constructed my bijective map. Now for the converse direction, suppose there exists a bijection f from x to y, and I want to show that they have the same cardinality. Now since y is finite, there exists a bijection by from y into the numbers from 1 to n for certain n. And then we can define a bijection from x into the numbers from 1 to n. Again, basically using the same idea here by composing the bijection by with the bijection f, which is given in this case, and this results in a bijection bx. And it follows from this that the cardinality of x is n, because we have a bijection from x to the numbers from 1 to n, and also the cardinality of y is n, because we have this bijection. So they have the same cardinality, and that concludes the proof for this direction and the proof overall of the proposition. Next, we show that the cardinality of two disjoint finite sets x and y, if we take their union, is just the sum of their individual cardinalities. Okay, so if we throw two disjoint finite sets together, then the number of elements in this collection is just the sum of the number of their individual elements. Now let's say n is the cardinality of x and m is the cardinality of y, and there are bijections because they are finite from x to the numbers 1 to n and from y to the numbers 1 to m. And now we define a map from their union as follows. From f from x union y to the numbers from 1 to m plus n, so the sum m plus n. And every element from this union is mapped as follows. If z is actually an element of x, then we just apply bx to it, so it gets mapped to the numbers from 1 to n. And if z is an element of y, then what we do is we take its image under the bijection by, so we get a number from 1 to m, and then we add n to it. So here we get a number from n plus 1 to m plus n. And then we already see that the values that are assumed for elements of y are all strictly greater than the values that are assumed for elements in x. And this map is well defined because we assumed that the intersection of x and y is empty, because we assumed they're disjoint. So if we had an element that was contained in both x and y, then we would get conflicting definitions for this element here, because both definitions of f would apply to it and they would be contradictory. So if this was not an empty intersection, we would not get a well-defined map with this assignment here. But because we assumed this from the beginning, it's okay to define f like this. And now I want to show that this map f is bijective. And I do this by stating an inverse map for f. And again, recall, f having an inverse map is equivalent to saying that f is bijective. And the inverse map is defined as follows. I simply undo what I did here. I map the elements from 1 to m plus n as input values to the union of x and y. And every element j from this set here, if it's less or equal to n, I map it to bx inverse of j. And if it's greater than n, then first I subtract n. By doing so, I move it to the value range from 1 to m. And then I apply by inverse to it. And you can look at it for a while to see that this in fact does reverse the function f. So imagine if I plug in a value of x here, then it spits out a value between 1 and n. And if I apply f inverse to that, then the first rule here would apply, and I would just take the inverse of bx again, and I would end up with my original element z. And if the element came from the set y under f, I would compute by of z and add n to it. So I would get a number larger than n. So if I apply f inverse to that, the second rule here would apply. That means I would first subtract n again, and then I would apply by inverse and thus recover the original element z again. And this means, well, you have to check it from the other side as well, but you can do that as an exercise yourself. But this means that f inverse here is indeed the inverse map for our f here. And this means f is bijective. And now it follows that the cardinality of the union is m plus n, because we have a bijective map from it into this set here. And m plus n was just the sum of the respective cardinalities of x and y. Now we have a consequence of this, corollary 12. If x is a finite set and x0 is a subset of x, then the cardinality of the subset is at most the cardinality of x. So intuitively, this is again something that's completely clear. If we take a subset from a finite set, then of course, how should it have more elements than the original set? But we have to give a formal proof for this. And the equality of the cardinalities holds only if x0, if the subset is actually already the full set. So for proper subsets, we would have a strict inequality here. Now, we've proved before in Theorem 6 that the subset of a finite set is finite, so we know x0 is finite. And of course, if x0 is identical to x, then this is trivial because it's the same set, which of course has the same cardinality as itself. So we assume now that x0 is a proper subset, so there exists some element in x0, some element in x, that is not contained in x0. If x0 is the empty set, then there's nothing to prove because its cardinality would be 0 and this would be satisfied. So we assume x0 is not the empty set. And then we can look at its complement in x, call this x1, which is x without x0. And this is also a non-empty proper subset of x, and this is disjoint from x0. So we have two disjoint subsets, x0 and x1, of our set x. And by the previous Theorem 11, we can now apply this formula here. The cardinality of x is the same as the cardinality of x0 plus the cardinality of x1, because they're disjoint. And they're both not empty, so both of these cardinalities here are strictly greater than 0, they're positive. But this means, if we transform this equality here, the cardinality of x0 is the difference of the cardinality of x and the cardinality of x1. And because this is positive, it's strictly smaller than the cardinality of x. And this is what we wanted to prove. For proper subsets, the cardinality is strictly smaller and equality only holds if the sets are identical. Now let's have a fact about finite sets and maps. Here we take two sets x and y and we allow y to be any set, so we don't assume that y is finite. It could be finite, it could be infinite, we don't care. But x has to be a finite set, and we have a map f from x to y. Then, x being finite, the image f of this map is also finite, and the cardinality of the image is less or equal the cardinality of x. So if I take a finite set as input values for a map, then there are at most as many output values as I had input values. That's also something that's intuitively quite easy to believe. And the equality here only holds if f is injective. If and only if f is injective, I should say. Okay, so if f is not injective, then this is a strict inequality. We prove this by induction on the cardinality of x. The initial case being that x is the empty set, there's nothing to prove because there are no maps from the empty set into other sets. The induction hypothesis is that this proposition holds for all finite sets with cardinality less or equal to n for a certain number n. Now, for the induction step, we consider a set x with cardinality n plus 1. And we pick one element x0 in x, and we look at its complements, which I call x index n. So this is x without the element x0. Then, by proposition 11, the cardinality of xn equals n, because x has cardinality n plus 1, we take one element away, so the set with x0 in it and the set xn are disjoint, so their cardinalities add up to n plus 1. And because this has one element, xn must have cardinality n. So by the induction hypothesis, which now applies to the set xn, the cardinality of the image of f restricted to xn is less or equal to n. But now the image of f is the union of the image of f restricted to xn and the value of f applied to x0. This is not necessarily a disjoint union. We can't say that at this moment, but nevertheless this is true, this equality here. So it follows that the cardinality of the image of f is the cardinality of this set, because these two sets are identical. And, well, this set here can have at most n plus 1 elements, because there are two possibilities. Either f of x0 is already contained in image f restricted to xn, then it would have less or equal n elements, or this f of x0 is not contained here, then it's a disjoint union, and then we have one cardinality here plus the cardinality of this, which is less or equal to n, so the whole thing is less or equal to n plus 1. But this is the cardinality of x. And this proves our inequality here. Now, as for the injectivity, f being injective is equivalent to f restricted to xn being injective, and f of x0 not being contained in the image of f restricted to xn. Now we can apply the induction hypothesis and proposition 11 because, well, the image of this and this one are disjoint sets, so proposition 11 applies to their cardinalities, that we can just add them. And the induction hypothesis now tells us, because f restricted to xn is injective, that its cardinality is in fact equal to n. So the cardinality of the image of f, because it's now the disjoint union of the two, is n plus cardinality of this, n plus 1. And this proves the final statement in our proposition. And another proposition we want to prove about maps between finite sets. So x and y are both finite sets again now, and f from x to y is a map. And we assume now that both x and y have the same cardinality. And then the following statements are equivalent. And that's quite interesting. Because first, f is injective, f is surjective, and f is bijective. These are all equivalent, so we know that if f is injective, then it must already be surjective, which of course means it's bijective, and vice versa. If f is surjective, then it must automatically be injective if the cardinality of domain and codomain are the same. And to prove these equivalences, we will prove them in this order. We will prove that 3 implies 1, which is actually trivial, that 1 implies 2, and that 2 implies 3. So we go from 3 to 1, from 1 to 2, and from 2 to 3, and then we have seen that all of these statements are equivalent. As I said, from 3 to 1 is trivial because any bijective map is also injective by definition, so there's nothing to prove here. Now we go from 1 to 2. We suppose, number 1, that f is injective, and we want to show that it is surjective, which then automatically makes it bijective, of course. If it is injective, then f is bijective onto its image in y, so imf, subset of y. And by what we learned before, this means the cardinality of x is equal to the cardinality of the image of f. But we assume that x and y have the same cardinality, so this means that the cardinality of y equals the cardinality of the image of f. And since the image is a subset of y, it follows from corollary 12 that y equals the image of f. A subset which has the same cardinality as the total set must be the total set already. But if y is all of image f, this is nothing else but saying that f is surjective. So we've concluded that if f is injective, f must be surjective. Now we assume that f is surjective and prove that it is bijective. If it is surjective, then, as before, the image of f equals y. And because x and y have the same cardinality, x has the same cardinality as the image of f. And by proposition 13, now this means f is injective. And because we already assumed it to be surjective, this means f is bijective. And that concludes the proof of these equivalences. Now that we've learned a few things about finite sets, we are going to learn a few things about infinite sets. And in fact, we can transfer some of the notions of cardinality to these sets and also compare their sizes in this way. Now, we call the set infinite if it is not finite, and you probably have seen the symbol of this loop or this tupled 8 being used to denote infinity. And just for history, this symbol was introduced in 1655 by the mathematician John Wallis and has been used ever since. But this symbol is not a number that we could use in computations, and usually when we use the symbol, it's just a convenient abbreviation to express something more complex. For example, that something is not finite or that something is not bounded. Also, it leaves open the question if there are different kinds of infinity. So is there only one kind of infinity, or are there different kinds of infinity? And if so, which one do we mean when we use this symbol? But we also want to compare the sizes of infinite sets, and even though we cannot assign a number to them like we did with the cardinality of finite sets, where the number is simply the number of elements, but we will see that certain statements about the cardinalities of infinite sets make sense, at least when viewed relative to other sets. So we say two arbitrary sets x, y are equinumerous if there exists a bijective map f from x to y. By proposition 10, we've already seen that finite sets x, y are equinumerous if and only if their cardinalities are identical. So that is pretty much what you would expect from something being called equinumerous. And symbolically, this relation can be extended to infinite sets. Now here's the definition for this. So x and y are sets. If there exists an injective map f from x to y, then we write cardinality of x is less or equal cardinality of y. If there exists a bijective map f from x to y, then we write cardinality x equal cardinality y. And as you would expect, if the cardinality of x is less or equal cardinality of y, but the cardinality is not equal, then we write this sharp inequality. So cardinality of x strictly less than cardinality of y. And for finite sets, these are actually statements that we proved in the previous section. But by making this definition here, we can make the analogous statements about infinite sets. And there's already a small exercise for you, so pause this video for a few minutes and prove the following two statements, the transitivity, if you like, of the cardinality order. So if we have three infinite sets ABC, then if cardinality A is less or equal cardinality B and cardinality B less or equal cardinality C, then also cardinality A less or equal cardinality C. And here the analogous statement, but with equality each time rather than less or equal. Okay, so I hope you gave this a few minutes of thought. And here's the solution, which is rather simple from the definition. So cardinality A less or equal cardinality B means there's an injective map f from A to B. Cardinality B less or equal cardinality C means there's an injective map G from B to C. And now we can form the composition of the two maps, G composed with F, which goes from A to C. And this is injective because it's a composition of two injective maps. And so we have an injective map from A to C, and that means, by definition, cardinality A less or equal cardinality C. And for the second part, you can use exactly the same argument where you replace injective with bijective each time. And we start our study of infinite sets and their cardinalities right out with one of the deep theorems on this subject. This is the so-called theorem of Cantor-Bernstein, which was also proved by Dedekind. And it states that if x and y are sets, such that cardinality x is less or equal cardinality y, and also conversely cardinality y less or equal cardinality x, then cardinality x is equal to cardinality of y. Now for finite sets this seems pretty obvious, but with our given definitions for the cardinality of infinite sets, this is not so obvious. And the proof is actually quite difficult and long, so it's worth to take the time to understand it and perhaps rewind the video in some places if necessary. Now, as for the name, originally it was proved by Cantor and Bernstein, and later it was found that Dedekind already gave a proof even before that. And often you will find it called Cantor-Bernstein-Schröder theorem, but Schröder's proof actually turned out to be incorrect, so maybe it's not appropriate to use the name here. Let's begin with the proof. So the assumption is this and this. So the assumption translates into there being injective maps f from x to y and an injective map g from y to x. And what we want to show is that there exists a bijective map h from x to y. Now, there's a construction here that's a bit complicated, so follow it closely. We define a certain subset A of X inductively by the following recursive rule. We start out with the subset A0, which is the complement of the image of G in X. And then, once the set AN in this sequence is defined, we define the set AN plus 1 by taking G of F of AN. And since we give A0 beforehand, then we can recursively define all the other sets in the sequence, such as this. And finally, we define the set A to be the union over all of these sets AN, beginning with the first set A0 and then all the sets constructed in this manner. And now we define a function from x to y, h from x to y, which is going to be our bijective map. And we define it as follows. X from the set big X is going to be mapped to f of x if x is an element in A. So if x is an element in this set, which in particular means that x is contained in one of these sets AN for some number n. And if x is not contained in A, if x is in the complement of A, then we apply G inverse to x. Now, why can I even say G inverse here? After all, we only assumed that G is injective but not bijective. But recall from the last chapter on sets and maps that G is bijective onto its image in X. So G inverse makes sense if X actually lies in the image of G. And this is what we're going to confirm first. So we are going to verify that this H is indeed a well-defined map from X to Y. This is the next step. So here I just repeat the definition of the set A and the map H in the small print. And I'm going to prove that H is well defined. So G is by assumption injective. So we can take the inverse G to the minus 1 on the image of G in X. Now, by construction, the complement of A in X is contained in the image of G. So the element G inverse of X in the definition of H exists. So this is contained in the image of G. So we can apply G inverse to it. And this means the map H is well defined. So let's take a moment to ponder this. If X is not in A, if the element little x is not in A, what does it mean? Well, the image or the complement of the image of G is A0 by definition. So the complement of the image of G is contained in A. In other words, every element in X, in the set big X, that is not in the image of G is contained in A. But that in turn means every element that's not in A must be in the image of G. Okay? And this is just what I stated here. The complement of A in X is contained in the image of G. So we proved that H is a well-defined map, and now we're going to prove it is bijective, and by that I mean, of course, we prove that it is injective and that it is surjective. First we prove the injectivity. So what we need to show is for two elements, x1, x2 in the set big X, we show that if h of x1 equals h of x2, that this implies x1 equal to x2. So no two distinct elements can be mapped to the same value under H. The first case, because we have definitions separately for x in A and x in the complement of A, the first case is when both elements are elements of A, x1, x2 in A, then both of them are mapped by H using the map F, but F is injective by assumption, so this follows by the injectivity of F. The second case is that both of them are in the complement of A, x1, x2 in X complement A, and then this case applies, so we applied G inverse to x1 and x2, and now this follows from the injectivity of G, because if G is injective, then also its inverse map, G inverse, is injective. So G inverse is injective, so it follows in this case also that x1 and x2 have to be the same element if they assume the same value under H. And now what remains is the case that one of the elements is in A and one of the elements is in the complement of A. So say x1 is contained in A, x2 is contained in the complement of A in X. And we assume that they take the same value under the map H. And what we will show is that this actually cannot happen. This leads to a contradiction. So x1 being in A is mapped by H to fx1, and x2 being in the complement is mapped to G inverse x2. So this equality here means f of x1 is equal to G inverse of x2. Or equivalently, if we apply the map G to both sides of this equation, we get G of f of x1 is equal to x2. Now, x1 is an element of A, and x2 is not an element of A. If x1 is an element of A, it is contained in one of these sets AN, and so applying GF to it by this definition here means that the left-hand side is contained in some of the sets AN plus 1. So since X in A, we also have that G of f of x1 is in A by construction of the set A. But the assumption was on x2 that x2 is not an element of A. So we have a contradiction here. On the left-hand side, we have an element of A, but on the right-hand side, we assumed that x2 is not contained in A. So this situation here cannot happen, that x from A1 and x2 from X complement A assume the same value. This cannot happen. So the only cases that could happen are the two cases up here, and in this case H is injective, and so overall we found that H is an injective map. And the next step is now to prove that H is surjective as well, and then we're done once we've shown this. So in order to prove surjectivity, pick any element y in the set big Y, and we will show that y is contained in the image of H. Now, what can we do with an arbitrary element y? We can apply the map G to it, which maps it back to X. So if gy, which is now an element of the set X, is not in A, then applying H to this, H of G of Y, becomes G inverse of G of Y by this part of the definition of h here. So here we have x equal to gy, and if it's not in A, then this part of the definition applies. So g inverse g of y equals y. But this just means that y is contained in the image of h, because g of y gets mapped to y by h. So this case is good. And the other case is if gy is actually contained in A. So then we would have to apply this part of the definition, and we couldn't that easily conclude that y is in the image. But if gy is contained in A, then there's some index n such that gy is contained in an. And in particular, we can say that n has to be larger than 0, because by definition, a0 is the complement of the image of G. But of course, the element gy is an image under G, so it has to be in the image of G. So it can't be contained in a0, but it has to be contained in one of these higher index ans. But if it's contained in one of these higher index ans, it means that there must be some x in an minus 1 that gets, by this construction here, mapped to gy. So gy is equal to gf of x, where x is taken from an minus 1. And now G is invertible on its image, so we can apply G inverse on both sides here. So this means y is equal to f of x for this particular x here. But this x from an minus 1 in particular is in A, so applying f of f to this x is the same as applying h to x. So again, we found that y is contained in the image of h. This means h is surjective, and all combined, it being injective and surjective, that proves that h from x to y is a bijective map. And this concludes the proof of the Cantor-Bernstein theorem, that if we have an injective map from x to y and an injective map from y to x, then there must be a bijective map between the two. And here's another exercise for you where you can try out a little bit finding injections between infinite sets. So here we have two intervals. First we have the open interval from 0 to 1, which is all real numbers between 0 and 1, but excluding 0 and 1. And next, the set B is the closed interval from 0 to 1, which consists of all the real numbers between 0 and 1, including 0 and 1. And you have to show that these two have the same cardinality. And obviously, you should use the theorem of Cantor-Bernstein to do this. I hope you thought about it a little bit. So here's a solution without too many explanations. What we need to do, according to Cantor-Bernstein, is we need to find an injection from A to B and an injection from B to A. And if we have that, then we can, by the Cantor-Bernstein theorem, conclude that they have the same cardinality. So first, an injective map from A to B is simply given by the inclusion map, because A is actually just a subset of B. The only elements missing from A are 0 and 1. All other elements from A are already included in B, so we simply map every element of A to itself. The inclusion map A into B is clearly injective. And another injective map in the other direction, from B to A, is given as follows. The idea is, well, we take every x from this closed interval, and then we shrink the whole closed interval from 0 to 1 to the interval of 0 to 1/4 by dividing by 4. And then we push this shrunk interval into the middle of the open interval by adding 1/2. And this is also an injective map. And so we found an injective map from A to B and one from B to A. And now by Cantor-Bernstein, we can say that the cardinalities of the open and the closed interval from 0 to 1 are identical. Let's look at some examples for infinite sets and their cardinalities. Here we have the natural numbers, and with 2n the even natural numbers. So this is a set of 2 times n for any n in the natural numbers. And these sets are indeed equinumerous. I get a bijection between them simply if I multiply every element n by 2. And the inverse is then, of course, dividing every element by 2. That's pretty straightforward to see that this is a bijection. And in a similar way, you could show that n and the odd numbers, all the numbers 2n plus 1 with n in the natural numbers, are equinumerous. So n and the even numbers in n have the same cardinality. And also the natural numbers and the integer numbers are equinumerous. We can define a bijection f from n to the integers by mapping 0 to itself, then mapping 1 to -1, 2 to 1, 3 to -2, 4 to 2. So all the odd numbers get mapped to the consecutive negative numbers, and all the even numbers get mapped to the consecutive positive numbers. If you want to write this out more explicitly, this bijection is given by this expression here. N maps to n over 2 if n is even, and it maps to n plus 1 over 2 minus if n is odd. And in this way you cover all the positive and all the negative numbers in the integers with this map from the natural numbers. So this is maybe, if you see it for the first time, a bit counterintuitive, because you could clearly say n is smaller than the integers z, in the sense that there are a lot of elements here that are not contained in n. But at the same time, it's not smaller because you have a bijective map between the two. So that's one of the weird properties of infinity. Something like that you will actually encounter quite often. But you just have to accept it, that infinity does not always cater to our intuition. The next example is perhaps rather surprising. Here we have that the natural numbers and the rational numbers are in fact equinumerous. So we can find a bijective map from the set of natural numbers into the set of fractions. But to see this is actually quite a bit of work. So we will proceed in 2 steps that each for its own is actually quite involved. So first we will construct a tree, so an abstract tree structure whose vertex set coincides with the positive rational numbers, which I denote by q+. And then I will assign an integer in binary representation to each vertex of the tree, and will thus obtain a bijective map from the vertex set to the positive natural numbers, which are just all the natural numbers except for 0. The tree construction is rather simple, so it works as follows. The root vertex in our tree is the rational number 1, and then for any vertex in the tree that is a reduced fraction p over q in q+, we have a left child vertex that is p over p plus q, and a right child vertex that is p plus q over q. So it looks like this. And in particular, note that the left child vertex is always smaller than the parent vertex, and the right child vertex is always larger than the parent vertex. What do we do with this now? So the tree we construct in this manner will look like this, at least the top part of it. So on level 0, we begin with the vertex 1. On level 1 we have 1/2 and 2 over 1, so 2. On level 2 we get 1/3, 3/2, 2/3 and 3, and so on. So by the level in the tree, what do I mean? I mean the number of edges you have to traverse to get back to the root vertex. This is the level of a vertex in the tree. And the tree of this kind is called a Calkin-Wilf tree. And we prove that the set of these vertices, when we take them as rational numbers, is precisely the positive rational numbers. First, we convince ourselves that every fraction constructed by the aforementioned method is in fact again a reduced fraction. Now this is true for the root node here, 1 over 1 on level 0. And now we may suppose, by using induction, that this is true up to level n in the tree. Now assume on level n plus 1 there's a non-reduced fraction p over q. Then p and q must have a common divisor d, and this d is greater than 1 because we assume they're not reduced. Now if our non-reduced fraction p over q is a left child in the tree, then the parent vertex is p over q minus p, simply by reversing the construction rule for the child vertices in the tree. And this parent is located on level n in the tree if p over q was on level n plus 1. And this common divisor d also divides p and q minus p. But if p over q is a right child in the tree, then the parent is p minus q over q on level n again, and the common divisor d also divides p minus q and q. So either way, it contradicts the induction hypothesis for level n, because we assumed on level n that only reduced fractions appear, but the parent vertex in either case would also be a non-reduced fraction. So this contradicts the induction hypothesis, and therefore it cannot happen that a non-reduced fraction appears on level n plus 1. By induction, it cannot happen overall in the tree. So all fractions are reduced. Now we prove that the set of vertices is precisely Q plus, the set of positive rational numbers. First, we prove that every rational number p over q appears in the tree, and then next we will show that every number appears exactly once. So number 1 occurs, it's just the root in our tree. And now suppose there exists some fraction, some reduced fraction p over q in q plus that does not appear in the tree, and suppose among all of these fractions it is the one with the smallest denominator q, and among those the one with the smallest numerator p. Now if p is larger than q, then also p minus q over q cannot appear in the tree, because if it did, then it would have p over q as a child vertex. But we assumed this doesn't happen, so p minus q over q cannot appear in the tree either. But the numerator p minus q is smaller than p, which is a contradiction to our choice of p over q, where we assumed that q is minimal and the p is also minimal among those with minimal q. And similarly, if we assume that p is less than q, then p over q minus p cannot appear in the tree. But here q minus p is smaller than q, which again contradicts our assumption or our choice of p over q. And now the case p equal q, of course, we don't have to consider because that would correspond to the root vertex. So in any way, we found a contradiction to the assumption that p over q does not appear in the tree. So that means every p over q in q plus must appear in the Calkin-Wolf tree. And now we prove that each occurrence is unique. So every p over q appears precisely once in the tree. We already know from the previous step that it does appear. And it's easy to see that one cannot appear as a child for any fraction p over q. And this is simply because by the construction rule, for the tree children, we can never get a fraction of the form p over p. So one can only appear here. Now, suppose by induction on the levels that no fraction up to level n appears twice in the tree. But suppose that some fraction p over q on level n plus 1 appears somewhere else in the tree. Now, what does this mean? First, the second appearance of p over q cannot have the same parent vertex as this p over q here, because the two child vertices of one vertex in the tree are never identical. Because the left child is always smaller and the right child is always larger than the parent. So there's a parent vertex on level n of p over q, and this must also appear twice in the tree. Why is that? Well, depending on whether p is larger than q or smaller than q, p is a right or a left child of its parent, and that is true for every occurrence of p over q in the tree, simply from the construction rules for the tree vertices. And if we know it's a left child, or respectively if we know it's a right child, then we also know what the parent vertex would look like, again by the construction rule in the tree. So if we know that p over q appears twice, then we also know that its parent vertex appears twice. But the parent vertex appears at least once on level n, because we assumed p over q appeared on level n plus 1. But this contradicts our induction hypothesis, because we assumed that up to level n, nothing appears twice in the tree. So in conclusion, no fraction can appear more than once in the tree. And this shows that every vertex in this Calkin-Wolf tree can be identified with an element of q plus, and the totality of vertices can be identified with the set q plus. Next, we constructed bijection from the Calkin-Wolf tree to the natural numbers n, or rather the positive natural numbers n plus. And actually this bijection would work to enumerate the vertices of any binary tree. And first we take a quick detour to review the binary representation of a natural number. You might be familiar with that, but just in case, I will quickly review this here. So every natural number n can be written uniquely in the following form. N equals 2k times bk plus 2k to the power minus 1 times bk minus 1 and so on, plus 2 times b1 plus 2 to the power of 0 times b0, where these b's, bk, bk minus 1 and so on, b1, b0 are all either 0 or 1. So you could think of these as the bits representing the natural number n. And we also use the notation n equals, and just this bit string bk, bk minus 1 will be b1, b0 with the index 2 for this. So this is just a shorthand notation for this. And to give you an example, let's take the number 23. We can write this as powers of 2. So this representation here is nothing but representing n as a sum of powers of 2. So 23 is 16 plus 4 plus 2 plus 1. So this is, to make it correspond to this notation here, this is 2 over 4 times 1, 2 over 3 times 0, plus 2 over 2 times 1 plus 2 over 1 times 1 plus 2 over 0 times 1. And in this shorthand notation, this is just 1, 0, 1, 1, 1, index 2. So we take the powers of 2 that appear here in the sum. That's 2 over 4, 2 over 2, 2 over 1, and 2 over 0. And multiply them by 1. And the ones that don't appear, which is only 2 over 3 here, is multiplied by 0. And then we take these coefficients here and just write them in the bit string here. So this is the binary representation of the number 23. Now let's get back to the proof. We know that we can identify the vertices in the Calkin-Wolf tree with the set Q+. And now comes the second step of our proof, that n and q are equinumerous. And that is, we construct a map from q plus to n plus as follows. First, we map the fraction 1 over 1 to the number 1. And then for any p over q in q plus, which appears as a vertex in the Calkin-Wolf tree, we construct the binary representation of a natural number f of p over q as follows. We begin at the root node, which is 1, the root vertex, and there's a unique path leading to the vertex p over q in the Calkin-Wolf tree. We begin with a binary number 1 at the root vertex, and on the path to p over q, every time we pass a left child, we append a digit 0 to the binary number. We append it on the right, so we attach it to this 1. And every time we pass a right child, we append a digit 1 to the binary number. So here, as an example, the first few levels of our tree, we begin with binary number 1 at the root. If we go left, we attach a 0. If we go left again, we attach another 0. If we go right here, we attach a 1. And if we go right here, we attach a 1. If we then go left, we attach a 0. Or we attach another 1, and so on. And you can already see that we are nicely enumerating all the binary numbers in this manner. So once we reach the vertex p over q, the resulting binary number is f of p over q. So that's the image of our map f here. Now we need to show that this is bijective. So keep this image here in mind. First we show it's injective. So if f of p over q is the same as f of r over s, then they both have the same binary encoding that translates into a path from the root to p over q and to r over s. But it's the same path, so it leads to the same node, and that means p over q is the same as r over s. And this means f is injective. And now, given any natural number n that is greater than 0, let this bit string bk to be 0 be its binary encoding. And we have to show that this is indeed in the image of f. But yeah, this encoding just translates into a path in the Calkin-Wolf tree, starting at the root, and then turning left if the consecutive digits here are 0, and turning right if the digit is 1, going from the left to the right. So the first digit bk is 1, that stands for the root node, and then we turn, depending on what comes next, left or right, and so on until we do the last turn, and this leads us to some vertex p over q in the tree. But this means nothing else that f of p over q is n by definition of f, and this means f is surjective. So it follows that f of q plus to n plus is a bijective map. And now I'll leave it as an easy exercise to extend this map f to a bijective map between the full rational numbers and the natural numbers including 0. And this shows that we have a bijection from the rational numbers to the natural numbers, and we have proved that n and q are indeed equinumerous. Now, we've seen that several sets are equinumerous to n, and any set that satisfies this condition is called countably infinite, because, well, it's infinite because n is infinite, but it's also countable because we can count stuff by using bijections from n. And a set that is either finite or countably infinite is called countable. And now if there are any sets that are not countable, so neither finite nor countably infinite, then we shall call them uncountable. And we introduce this symbol here, Aleph 0, so Aleph being the first letter in the Hebrew alphabet, and Aleph 0 denotes symbolically the cardinality of the natural numbers. And in set theory there are certain symbols, Aleph 1, Aleph 2 and so on, which represent higher types of infinity, but the definition goes too far to be covered in this course, so we will not do this here. But such symbols can be used conveniently to compare the sizes of infinite sets, and we can use them to some degree as if they were numbers. And thus they're also called cardinal numbers. And in this newly introduced language here, the previous examples have shown what I summarize in this theorem here. The cardinality of the even numbers, even natural numbers, and the cardinality of the integers, and the cardinality of the rational numbers are all Aleph 0. Or in other words, all of these sets are countably infinite. And as a rather quick exercise for you, you can prove that if x and y are both countably infinite sets, then there exists a bijective map between x and y. So I hope you quickly did this. And since both these sets are countably infinite, we have bijections f from x to n and g from y to n, and then we can simply compose the inverse of g with f, and we get a bijection from x to y, which was required here. In the next example, we will show that the cardinality of the real numbers is strictly greater than the cardinality of the natural numbers, which means that the real numbers are an uncountable set. The proof uses a trick known as Cantor's diagonal method, and we do a proof by contradiction. So we assume that the real numbers are countably infinite. We already know they are infinite, so we assume they are countably infinite now. And then the subset 0, 1, so the open interval from 0 to 1 in the real numbers is also countably infinite. We use this fact without a proof. It can be proved that the subset of a countable set is always countable itself, but I'm not going to do this in this course. So we just accept this. Now, if this is countably infinite, there exists a bijective map for f from the natural numbers into the open interval from 0 to 1. And we can write this as follows. The element f of n is written as a decimal expansion, so 0 dot dn0, dn1, dn2, dn3, where d and j is the jth decimal digit for the number fn. So these digits are all numbers between 0 and 9. And of course here the leading 0 because we are strictly between 0 and 1. Now we construct the number x with decimal digits x0, x1, x2 and so on as follows. X equals 0 dot x0, x1, x2, blah, 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 where we choose the nth digit of x to be 2 if dnn is not equal to 2, and to be 3 if d and n is equal to 2. So for the nth digit of x, we look at the nth digit of fn, and then depending on whether it's 2 or 3, we pick xn to be at least something different. Because x constructed in this way is also an element of the interval from 0 to 1, there must exist some natural number m such that fm is equal to x. But by our construction, the mth digit of x is not equal to dmm. But dmm should just be the mth digit of f of m, so the mth digit of x. So we arrive at a contradiction, and this means R has to be an uncountable set. Next, I want to give a very interesting characterization of infinite sets. So we have seen in the examples that the natural numbers and the integers are equinumerous, and also equinumerous to some other sets. And in particular, we see that these are equinumerous to some of their proper subsets. And I want to prove that this property, being equinumerous to a proper subset, is characteristic of infinite sets. First, I will prove this lemma here. Every infinite set X contains a countably infinite subset. Irrespective of whether X is countably infinite or uncountable, it always contains a countably infinite subset. And I will only sketch the proof for this lemma. So we begin by picking any element x0 in X and form the set C0, which only contains this single element. And then inductively we can form further subsets. So assume we are given a finite subset Cn of X with n elements, more than one, greater or equal 1. Then we can always pick another element xn plus 1 in X that is not contained in Cn already. And if this were not the case, then, well, then every x would already be contained in the finite set Cn, and that would be a contradiction to x being infinite. And then we define the set C to be the union over all these finite sets Cn, the union from C0 over all the Cn's constructed iteratively in this way, and this is just a set containing all the elements x0, x1, x2, and so on. And of course, we get a bijection from n into the set C by mapping n to the element xn. So this is a countable subset of X, and we have proved our lemma here. Now I only call this a sketch of a proof because there's a certain subtlety involved here with the picking of these elements xn plus 1. So this may sound trivial in the proof, but it is in fact, from a set theoretic point of view, not such a trivial issue. And indeed we have to require that the so-called axiom of choice is assumed, which essentially states that we're able to choose one element from every subset of X. I will say a few words on this later in this lecture. But now, with this lemma, I'm going to prove the following theorem. A set X is infinite if and only if it is equinumerous to one of its proper subsets. So for the proof, we have two directions. So first I do the direction from the right to the left. So I assume we have a proper subset, let's call it x prime of X, and we have a bijection from X to X prime, so they're equinumerous. And then I want to show that X has to be infinite. Now suppose X is finite. Then, by proposition 10 that we had before, X and X prime have the same cardinality because there's a bijection. And the proposition 10 on finite sets said that finite sets that are bijective to each other have the same cardinality. But also this contradicts our corollary 12 on finite sets, which says that a proper subset has strictly smaller cardinality than the full set. So we have a contradiction to the assumption that X is finite, and this means that X must be infinite. Now for the other direction, we suppose X is infinite, and by the lemma 22 that we just proved, we can pick a countably infinite subset C of X, so with the element x0, x1, x2, and so on. Now I define a map from F from X to itself, where I map every element either to itself if it's not contained in C, or if it is contained in C, I map it to the next element in C. So if it's x0, I map it to x1. If it's x1, I map it to x2. x2 goes to x3, and so on. And this map is, of course, surjective onto its image, x prime. And we have x prime is x without the element x0, because by this rule here, you see that there's nothing that ever gets mapped to x0. So x prime is indeed a proper subset of X. Now we show that F is injective as well, and we can see this because we have an inverse map, F to the -1, on the image of F. So this inverse map is given basically by shifting back all the xi's to their previous values. So x1 gets mapped to x0, x2 gets mapped to x1, x3 gets mapped back to x2 here. And all the elements that are not contained in C still get mapped to themselves. So nothing happens with them along the way. And since F is injective and surjective, it is actually a bijection onto X prime. And this means X is equinumerous to its proper subset X prime. And this concludes the proof that infinite sets are characterized by being equinumerous to one of their proper subsets. Now, as a little outlook, I want to get back to this axiom of choice that I mentioned before. So in the proof of the lemma we just had, we required a way of picking an element from every subset of X. And this can be done if we accept the so-called axiom of choice, which states the following. So we're given any set X of non-empty sets, so a set X whose elements are sets themselves. And given such a set, there exists a map F from X into the union of all the sets that are contained in X, that are the elements of X, in such a way that each set A in our collection X of sets is mapped to an element in A. That is, for all A in X, F of A is an element of A. That's a bit hard to get your head around when you see it for the first time, a set containing sets as element and then sets being mapped into themselves. But such a map F is called a choice function for X, and what it essentially tells us is if we have this collection of non-empty sets, there is a function that can, for every set in this collection, pick one element from this particular set. This axiom is not required when we're dealing with finite sets X, so with finite collections of sets, because then the existence of such a choice function can be proved inductively. And an important special case is when X is the power set of some set A, which we will define later in this video. And then this axiom states that we can select one element from each subset of A. And now I want to give you some final remarks on countable sets, without proof though, because the proofs are a bit technical and involved, so I will just state them here. First, every subset of a countable set is countable. The union of finitely many countable sets is countable, and the Cartesian product of finitely many countable sets is also countable. And if we accept the axiom of choice, we can replace finitely many by countably many in those two items. And usually one always works with the axiom of choice in mathematics. There's only some very fundamental areas of set theory where people do not necessarily accept it, but in most parts of mathematics people accept the axiom of choice as being true. One corollary from this proposition is that the set of so-called irrational numbers, which is the complement of the rational numbers in the real numbers, is uncountable. How does this follow? Well, we know that Q is countable, and if its complement was also countable, then the union of the two would have to be countable, but the union is just the real numbers and they are not countable. So that couldn't work. So the complement of Q in R has to be uncountable. And next up are power sets, a very important theoretical construct in mathematics. Now, what is a power set? If we're given any set X, then the power set Px of X is defined to be the set of all subsets of X. So the power set is a set whose elements are themselves sets. And sometimes you will see this curious notation here, 2 to the power of x for the power set. So this means exactly the same as this. And in a few moments we will see why this notation actually makes sense. But now we first look at some easy examples. So the power set of the empty set, P of empty set, is this, the set containing the empty set. Now why is that? Because every set contains the empty set as a subset, so even the empty set contains itself as a subset. So it appears as an element in the power set, but of course the empty set does not contain any other element, so no other subsets can appear, and so the power set has only one element, which is the empty set itself. And now please do not confuse this set with the empty set itself. The empty set is the set that does not contain any element, and that is not the same as the set that contains the empty set as an element. I know people often get confused by this, but please be careful that you don't fall into this trap. The empty set contains nothing. The power set of the empty set contains one element, which is the empty set. Next, we have a set x1 which has precisely one element, the number 1 in this case, and the power set of x1 has two elements, namely the empty set, because as I just said, the empty set is a subset of any set. And then the only other subset we can find here is the full set itself. So the other element in the power set is the set containing 1 itself. And now we have a set x2 which contains two elements, denoted by 1 and 2 here. And the subsets of this one are, again, of course, the empty set. And then we can form one subset which contains only the element 1. And we can form another subset which contains only the element 2. So they would appear here as two proper subsets of x2. And then again we have the full set x2, which is a subset of itself, so it also appears in the power set. And if you find it confusing to see sets within sets, then look at this. We can form the power set of x1, and this is the following. We have to focus. Of course, the empty set is a subset of any set, so it appears here. Then we had the empty set as an element of the power set. So now we have the subset. This one has the subset that only contains the empty set. And then we had the set that only contains the element 1 as a subset. So we can have the subset that contains as only element the set that only contains 1. And then we can take the full power set as a subset of itself, and this would be the power set here. Yeah, so this takes a bit getting used to, but it is quite logical, of course, like everything in mathematics. So take your time to study and understand it. Next, we have an example with 4 elements. Here I didn't use numbers, but the playing card suits. And actually, this is a nice exercise for you to do on your own now. So please pause the video and take a few minutes to list all the subsets of the set X here. I hope you gave it a try. So here's the power set of this set. Of course, the empty set is an element here. Then we can take 4 subsets which contain 1 element each. So 4 subsets that correspond to the individual elements of X. Yeah, and then we have to do a bit of combinatorics. We have several 2-element subsets here, 6 to be precise, and then we have 4 subsets with 3 elements. So these are all the possibilities where we can pick 3 out of 4. These are all the possibilities where we can pick 2 out of 4. And finally, we have the full set X as a subset of itself. And these are the elements of the power set. Now, if we look at this example, if we count the elements here, we have 1, 4, 6, another 4, and another 1. So these are actually 16 elements. And maybe let's quickly go back to the previous ones. Here we had 0 elements in the empty set and get 1 element in the power set. Here we had 1 element in the set and get 2 elements in the power set. Here we had 2 elements in the set and we get 4 elements in the power set. So these examples might lead us to suspect that a finite set with n elements has the power set with 2 to the power of n elements. And we will in fact prove this in a moment. And for the proof, I will use a particular map. I call it the characteristic map. And this can be viewed as a bit encoding for the subset of a finite set X, where we call x1 to xn the elements of big X. And this characteristic map I denote by the Greek letter chi, or chi, if you prefer, which maps an element of the power set, so a subset of X in other words, into the Cartesian product, the n-fold Cartesian product of the set that contains 0 and 1. So if you think of these as bit values, then this map takes a subset of X and maps it into an n-bit tuple. And we define it as follows. Each bit is set, so each beta I in this tuple is set to 1 if the ith element here, the ith element from X, is contained in subset A, and it's set to 0 if it's not contained. Okay, so we set the bit for each element that is contained in the subset A. So each subset will get mapped to a different tuple here, to a different bit encoding, if you like. And an example for this, for the set x2 with elements 1 and 2 from the previous examples, is the following. So we've seen that this is the power set of x2. These are the subsets of this set, empty, set holding 1, set holding 2, and the full set x2 itself. And because we have 2 elements in the original set, we map this to the 2-fold Cartesian product of the set 0, 1. So we get a 2-bit encoding with this map chi. And what happens? The empty set gets mapped to the tuple 0, 0, because none of the elements here, if this is x1 and this is x2, none of them is included in the empty set, of course, so both bits will be 0. The set 1, or the set containing 1, gets mapped to the tuple 1, 0, because the first element here is contained in this set, so we set it to 1, but the second bit corresponding to the element 2 that is not contained in this set is set to 0. And similarly, the subset containing only 2 is mapped to the tuple 0, 1. And finally, the full set, which contains all elements in our original set, gets mapped to the tuple with all bits set to 1. And this map we will use in the following proof of our suspicion here. Theorem 28 states that if X is a finite set of cardinality n, then the power set is also finite and has cardinality 2 to the power of n. And this explains what I mentioned in the beginning, that some people use the notation 2 to the power of x, where x is your set, to denote the power set of x, because it's suggestive of the fact that the power set contains 2 to the power of cardinality of x elements. For the proof, we write x as follows. We enumerate its elements x1 to xn and consider this characteristic map that I just introduced a moment ago, mapping each subset of x to a bit string where the nth or the ith bit is set if the ith element of of x is contained in A, and it's set to 0 if it's not contained in this subset A. We prove that this is bijective. Firstly, if A and B are subsets of X, then their image under the characteristic map, chi A equal to chi B, they're identical if and only if xi is in A is equivalent to xi being in B. Okay, they only get the same bit string if all the elements in I are in B and vice versa. But this is by definition nothing else but saying that A is equal to B. So if the values under the map chi are identical, then the sets are identical. So that means it's injective. And now for any bit string, beta 1 to beta n in the Cartesian product, n-fold product of set 0, 1, we consider the subset A that contains all the elements xi from the set big X, for which the bit beta I is equal to 1. And this is of course a legitimate subset of X, and by choice of A, this gets mapped to our given bit string beta 1 to beta n. So this is contained in the image. Any arbitrary bit string is contained in the image of chi, and this means chi is surjective. Together we have that chi is a bijection into this set, and the cardinality of the binary n tuples, so the n-fold Cartesian product of the set with two elements, is 2 to the power of n. So we had this more generally in one of the examples at the beginning of this video. And if we have a bijection from the power set of X into a set with 2 to the power of n elements, that means the cardinality of the power set is 2 to the power of n. And this concludes the proof. And as an exercise, you could try to do a proof by induction of this theorem. It's not too difficult, but I think this version is more elegant. Now we've just seen that the power set for finite sets is significantly larger than the original set. And is a similar thing true for infinite sets? Here we can't really assign numbers to the cardinalities, but perhaps we can still something about the power set being bigger. And indeed, that is the case. So if X is any set, then the cardinality of X is strictly less than the cardinality of its power set. And the proof is as follows. So we get an injection easily from X to its power set simply by mapping any element X to the set containing just this element. So this is of course a subset of the set big X, and yeah, it's clearly an injection from X into the set of all subsets of X. And having an injection from X into its power set means that the cardinality of X is less or equal to the cardinality of its power set. And we now prove by contradiction that no surjective map F from the set X into its power set can exist. And you will note in the proof that the idea works along the lines of Russell's paradox. And this is a bit of a brain twister, so make sure you follow the steps closely. So we assume, in order to derive a contradiction, we assume that there exists a surjective map F from X into its power set. Then we look at the following subset of X. I call it R, because Russell. R is the set of all elements in X, such that this element is not contained in its image under F. Okay, so F, the F of X here, is an element of the power set, so it's a subset of X. And we say these are all the elements in X that are not contained in this particular subset. X is not contained in the subset F of X. And the set of all these elements is a perfectly legitimate subset of our original set X, which means it's also an element of the power set. A subset of X must appear as an element in the power set. And we assumed that F is surjective, so there must be some element, little r, in the set X that is mapped to our set big R. So F of little r equals big R. Yeah, but now we're in this situation that is familiar from Russell's paradox. We use the definition of R against itself, if you like. If little r is contained in R, then by definition of R, that would mean that little r is not contained in F of little r, but F of little r is R. So if it's in R, then it must be not in R, a contradiction. But if we assume that little r is not contained in R, which is F of R, well, then again, it would follow that little r is an element of R, because R is just the set of elements that satisfy this relation. And again, we have constructed a contradiction. And therefore, it is impossible that such a surjective function F exists, and that means the cardinality of X is strictly less than the cardinality of its power set P of X. And that concludes the proof. Now we can say a bit more about how the cardinalities of the natural numbers and the real numbers are related. Namely, the cardinality of the power set of the natural numbers is identical to the cardinality of the real numbers. Recall that we've already seen that the cardinality of R is strictly greater than the cardinality of n. And we also know from the previous theorem that the cardinality of the power set of n is strictly greater than the cardinality of n. And here we see that the power set of n and the real numbers actually have the same cardinality, so they're equinumerous. And symbolically, we can write this as follows, that the cardinality of R is 2 to the power of R left 0, where recall R left 0 is the cardinality of the natural numbers. And we write this 2 to the power of course, as an analogy to the finite set case. Now I'll give you a sketch of the proof. I will gloss over a few details, but it shouldn't be too difficult to work them out. And I want to use the Cantor-Bernstein theorem. So what I want to do, I want to find an injection from the power set of n into the real numbers, and also an injection from the real numbers into the power set of n. And then Cantor-Bernstein will give me that there exists a bijection which will prove this theorem. So first, we know that the cardinality of n equals the cardinality of q. We've seen that in a rather lengthy construction in one of the examples before. And this implies that the cardinality of the power set of n also equals the cardinality of the power set of q. And in particular, this means there's a bijection, call it f1, from the power set of q to the power set of n. And I use this because to get the injection from R into the power set of n, it's easier to go via the power set of q. Namely, I will define the following injection f2 from the real numbers into the power set of q as follows. For any real number r, I define f2 of r to be the set of rational numbers that are strictly less than r. And this is a subset of q, of course, because I only pick rational numbers to begin with. And to understand why this map is truly injective, so that is why these sets here are distinct. If I take distinct values of r, we would need to look a bit deeper into the structure of real numbers than we have so far. But if we accept that real numbers consist of rational numbers together with the infinite decimal expansions, then we can easily find a rational number between any two distinct real numbers by looking for the first decimal digit where the two real numbers differ in their decimal expansion. And then we take the rational number whose decimal expansion coincides with the larger of the two real numbers up to this particular digit and then stops. And in this way, for any two of these sets with distinct values r, there will always be a rational number included with the larger one, but not the smaller one, and thus making the two sets distinct, which shows that the map is indeed injective. Okay, and now we can combine this injection with this one. So we take f to be the composition of f1 and f2, which goes from the real numbers into the power set of n. And we have our first injection here from r to the power set of n. And now we need one to go the other way. And we can recycle the idea of the characteristic map from the proof for finite sets in the following form. So I want to have an injection g from the power set of n into the real numbers. And I do this via a decimal representation for subset A of the natural numbers. I take the real number 0 dot d0, d1, d2, d3, where the d's are the decimal digits, which are simply set to 1. The nth digit is set to 1 if the element n is contained in the subset A. This is a natural number, so I can check if it's contained in the subset A from here. And I set it to 0 if n is not contained in A. And in this way, I construct the decimal expansion for a certain real number. And yeah, it's easy to convince yourself that for distinct sets, you get distinct real numbers because at some digit, the two have to differ because there will be some number that is contained in one subset but not in the other if they're distinct. And so in the corresponding nth digit, they will have a different value. And so we get two distinct real numbers, which makes this G injective as well. And now we have two injections, one in each direction. And so the theorem of Cantor-Bernstein tells us that a bijection between the two sets, power set of n and the real numbers, exists, which means that their cardinalities are equal. And that concludes the proof. And finally, some more thoughts on infinity. So we have seen now that there are different sizes of infinity. For example, cardinality of n, which we symbolically denote by r left 0, and the cardinality of the real numbers, which we now know to be 2 to the power of r left 0. And yeah, this gives rise to a few questions. For example, are there infinitely many types of infinity? And you could ask, how many infinities of infinity are there? And is there a cardinal number sitting strictly between r left 0 and 2 to the power of r left 0? So is there some set that has a size strictly between the natural numbers and the real numbers? And the first question is answered affirmatively by the theorem 29 on the power sets that we just saw, because we can always get a greater infinity by taking the power set. So, for example, from r left 0, we get a greater infinity by taking the power set of the natural numbers, which is 2 to the power of r left 0. Then we could take the power set of that to get an even greater order of infinity, and then again the power set. And we can do this with any infinite set. So whenever we have an infinite set, we can construct sets with strictly larger orders of infinity. Now for the second question, the negative of this question is known as the Continuum Hypothesis. And that's a conjecture that was formulated by who other than Georg Cantor in 1878. And yeah, it states that there is no set whose cardinality lies between r left 0 and 2 to the power of r left 0. So you cannot squeeze any infinity between the natural and the real numbers. And that is a question that bugged mathematicians for quite some time. And the, I would say, rather surprising outcome of this question is that we actually cannot give an answer. And it's in a way proven that we cannot answer this question, because in 1938, Kurt Gödel proved that within the usual framework of axiomatic set theory, the continuum hypothesis cannot be disproved. And then several years later, Paul Cohen proved in 1963 that the continuum hypothesis cannot be proved. So it neither follows nor contradicts the axioms of set theory. So it's kind of left dangling and cannot really be answered. And with this, I conclude this lecture. Thank you very much for your attention, and more math will be coming up soon.